All right, so good afternoon. I'm very happy to be here, so thank you very much for inviting me to this very nice meeting. I will continue the discussion on black hole hair, both from the classical and also from the quantum point of view, and I also try to explain you how this is related to Goldstone mode. So basically, this is also a continuation of two talks we heard yesterday by Andy Strominger and Malcolm Perry. Okay, the work is done in collaboration with Guy Advali, Cesar Gomez, and also Artem Avarin. And we had one paper last September, another one about half a year ago in January, and a more recent one now in June. So the outline is that I will start with an introduction, then I will talk about the black hole hair from the classical point of view, namely relating it to event horizon supertranslation, and finally I want also to discuss the quantum hair and the associated charges from black hole, and I will also use a particular toy model, I would say, where the black hole can be viewed as a graviton-bound state. I cannot resist showing you first a beautiful picture which shows the merging of binary black holes and the discovery of gravitational waves, namely the two spectacular events, one in September last year and the second one in December. Nevertheless, since black holes are visible in the sky, they are still mysterious objects, and there's in particular the question, what is black hole hair? Black hole hair can be defined as being kind of conserved asymptotic charges, and one assumes that the hair is carrying the information of collapsing matter that forms a black hole and subsequently evaporates via Hawking radiation. And hence, also this is not completely understood, the hair is supposed to provide a clue to the black hole loss of information puzzle. On the other hand, there is a famous classical black hole no-hair theorem that tells you that at the classical level there are no other charges than the mass, the electric charge, or the angular momentum of a black hole. However, quantum mechanically, one expects that the black hole is carrying a hair. So here we will consider purely gravitational hair as it is relevant for the most simplest black hole, namely the Schwarzschild black hole. And we try to understand first how the black hole hair can be understood from the classical point of view. And in fact, there is a proposal by Hawking, Perry, and Strominger that we heard about yesterday, that BMS transformations are responsible for the so-called soft black hole hair, and as it was explained also yesterday, it is related to the existence of soft gravitons. Our proposal is basically following this idea, namely, our proposal is that in addition to the BMS transformations at infinity, there is a non-uniqueness of the classical black hole metric due to event horizon supertranslations that we call A supertranslations, so basically acting with the generator of these A supertranslations on some given classical black hole metric, one gets another black hole metric. As we will discuss, the A supertranslations are spontaneously broken, and classically there exist infinitely many Goldstone modes of finite wavelengths, and hence the infinite, it leads therefore to an infinite classical black hole entropy. On the other hand, as we will also discuss, the associated charges are zero. On the quantum level, there is a non-uniqueness of finitely many almost degenerate black hole vacua, and correspondingly, the A supertranslation generators generate transition between the different black hole states. It is shown here. We will discuss that the A supertranslation group will be explicitly broken, and it follows that there are finitely many charges that correspond to finitely many pseudo-Goldstone bosons of finite mass. As we will discuss, at the quantum level, 1 over n corrections have the result that the charges are not anymore zero, they are non-vanishing, and this is also then relates nicely to a counting problem. As we will see, the entropy will be of order n, and there will be hence a finite quantum hair. And this proposal, as we will discuss, is then in accordance with the so-called soft 1 over n hair that was already introduced by Dvali and Gomez some time ago. So let me start with the gravitational black hole hair from event horizon supertranslations. Here are some basic definitions of the Schwarzschild radius, the Planck length, the entropy expressed in terms of Newton and the mass and h bar, and also the Schwarzschild radius. Basically, for the entropy, we will also often use not the symbol S, but N, by reasons that will become clear. And in fact, one can consider two classical limits. One classical limit where h bar is 0, and the mass and the Schwarzschild radius is kept finite. But there's also a semi-classical limit where h bar is finite, the Schwarzschild radius is finite, but G Newton is sent to 0 and m is sent to infinity. Both limits have in common that the entropy, that n goes to infinite. So we start with the Penrose diagram for the Schwarzschild metric, which I think is well known. This is singularity with two null surfaces in the past and in the future, denoted by sky minus and sky plus, and also the horizon. And as it was explained also yesterday, there are standard BMS transformations that act on sky minus or sky plus, and the corresponding Goldstone modes are modes of infinite wavelengths. In addition, there are also supertranslations on the horizon, as we will discuss. And here, as we will see, the Goldstone modes do not have infinite wavelengths. However, they have finite wavelengths. So basically, this is the outside of the picture. I'd like to discuss now in more detail and giving a few references. Supertranslations at the horizon were also recently considered by several people, which are written down here. Okay, what are supertranslations? Very briefly, these are, in the gravitational case, diffeomorphisms that keep the boundary, namely certain null surfaces of space-time metrics invariant. This is an old subject. In the bulk, they are viewed as gauge redundancies. So in the bulk, they shouldn't lead to physical charges. However, on the boundary, it can happen that they are not gauge redundancies, but they correspond to asymptotic symmetries, like large gauge transformations at infinity, which then also possibly provide physical charges. So for the black hole, we start with the Schwarzschild metric, not in the standard Schwarzschild coordinates, but in the Eddington-Finkelstein coordinates. So we have a radial coordinate, some retarded time v, which is a null direction, and two angular variables, which are hidden here in the omega square. So as I will now discuss, there are infinitely many massless modes of the black hole, at least classically. And we will in particular consider two kinds of metric transformations, which are called supertranslations or BMS transformations, namely shifting the time coordinate v by some function which depends on the angular coordinates theta and phi. One can consider two kinds of transformations, namely first transformations which act on the two surfaces at infinity. These are just the standard BMS transformations, and they act on the metric in a particular way, namely they act in the metric by a certain variation, which I have depicted here, and I have scaled out the radius as seen here, which means that we are considering, or that these transformations basically act in infinity. However, second, in addition, one can also construct and consider supertranslations, A-supertranslations at the horizon, and accordingly we parameterize the metric variations in the following way, where instead of R we have here just a constant Schwarzschild radius scaled out of the transformations. Okay, so first very briefly the supertranslation at sky minus. Doing those and performing those on the given metric which I have shown you, the modes, the metric variations have this form. They are given in terms of certain derivatives of the function f or g in this case. And the modes now correspond to soft gravitons, which are the Goldstone modes of the BMS transformations. They possess infinite wavelengths, and they denote in particular the infinite degeneracy of asymptotic flat spaces. The associated entropy formally is infinite, but it just means that the corresponding information is not really accessible, it is inaccessible. And as it was also discussed, they even act non-trivially on Minkowski space-time, which means that applying these transformations to Minkowski space-time, one can see immediately that there's an infinite family of flat Minkowski metrics. But second, now coming to the A supertranslations, which are supertranslations at the horizon. In fact, we have refined them slightly, and I could show you also the technical details by basically scaling out the soft modes from the translations, from the supertranslations at the horizon. So doing this, one gets that the corresponding metric fluctuations are given in terms of this matrix. And you see that the A supertranslations basically only act along the horizon on the directions of the two angular coordinates. They're also given in terms of derivatives, second derivatives of the function f. And these fluctuations, we call them the gapless Goldstone Bogoliubov A modes. In fact, they correspond to gravitational like waves, but not of infinite wavelengths, but of finite wavelengths, namely of wavelengths of order of the Schwarzschild radius, however, still of zero energy, so they are gapless. One can see this, and one can prove this, to show that these fluctuations keep the ADM mass of the black hole invariant, and one can also show that they are solutions of the full nonlinear Einstein equations at the horizon. Therefore, we propose that it is precisely, or there is precisely these A modes that should be identified with the microstate of the black hole and which are responsible for the so-called classical black hole hair. One can now, these transformations, in fact, generate an infinite dimensional algebra, and this infinite dimensional algebra is associated to infinitely many functions, and these functions can be decomposed simply in spherical harmonics, as it is written here, with certain coefficients in front of it, and classically the sum will run from zero angular momentum up to infinity. However, as one can also show, I think, very easily, the associated charges which are associated to these A supertranslations are all zero. This is easy to see. So the classical charges are vanishing if you perform this type of integral, which means that, again, according to our interpretation, the classical charges correspond to infinite entropy. However, it needs infinite time to resolve this information, and again, the classical information is not accessible. So this is indeed in agreement with the classical no-hair theorems. So now let's switch to the corresponding quantum picture. So now let me discuss the quantum hair and the charges of the black hole. And later on, also this is not immediately necessary, I will use the picture or the toy model of a black hole being a bound state of graviton. And at the end, I will also do some calculation in the coherent state picture. So if I have already shown you at the beginning, the metric variations now correspond to quantum mechanical generators. So we have generators noted by TA, which act on the black hole state, which corresponds to a given classical metric in the way that it corresponds one black hole state into a new one. As we will discuss now, unlike in the classical case, the quantum hair will become finite, and hence the entropy S or N respectively also becomes finite. In addition, unlike the classical case, we will see that we have a finite number of non-zero charges. And indeed, the idea is also this is not completely shown at the end. These charges measure the capacity to resolve the hair, and at the end they should be related to the black hole information puzzle. So there are two questions which I want to discuss now briefly in the following. How does the quantum hair become finite? And also, how many angular Bogoliubov modes must be counted as information carriers? And we will see that the counting is at least in agreement with the area law of Hawking. So to do this, one needs a microscopic picture, a microscopic quantum picture for the black hole. And as I will discuss now, in this quantum picture, it will turn out that unlike before, where the Goldstone modes were massless in the classical case, now in the quantum case, they will develop a finite energy gap, and hence there will be a finite energy gap between the different black hole vacua. It means that the A supertranslations are explicitly broken, so the A modes are collective finite gap excitations of gravitons that we call Bogoliubov excitations, and they are not anymore true Goldstone bosons, but only, however, so-called pseudo-Goldstone bosons. And in fact, as I have also mentioned before, this agrees with the picture of a black hole as a bound state of n soft gravitons at a so-called quantum critical point. So let me discuss this a little bit more in detail. It was shown in papers by Dwali and Gomez, and also by students of them. One can develop a model, a toy model, for example, a linear model, which shows many features that one expects for a black hole. In particular, that there's a quantum critical point at leading order in n, where all the different energy levels collapse and the system becomes gapless. In order to see this, one introduces a collective coupling. Alpha is basically the weak gravitational coupling, which denotes the coupling between the individual gravitons. N are the number of gravitons in the BEC, in the Bose-Einstein condensate. And in case this collective coupling is tuned to 1, the Bose-Einstein condensation takes place. So the energy which one can compute goes to 0, namely precisely when alpha is of the when alpha times n is of the order of 1. However, one can also compute for finite n subleading corrections to the energy gap, and then you will see that in order 1 over n, measured in terms of the Schwarzschild radius, the states are not completely degenerate anymore, but there are finite corrections which generate a finite energy gap such that the different frequencies are split of the order of 1 over n. Okay, so this is basically enough for us to construct the 8 charges and the different black hole vacua. In the quantum theory, the A modes are now given in terms of operators of finite wavelengths. So following the classical picture, these modes are given in terms of quantizing the coefficients B and B dagger, which are now annihilation and creation operators of collective graviton modes. One can even formulate an effective action on the horizon. Important is that we now have non-vanishing frequencies which go along with the annihilation and the creation operators. So there's a non-trivial V or time dependence. And now if you compute the charges, you will see that the corresponding integral is not anymore 0, but it is given by this expression in terms of the annihilation and the creation operators B and B dagger. So one can make this even a little bit more explicit, representing the black hole as a coherent state of the corresponding B modes of the corresponding Bogoliubov modes, so making particular ansatz of this form. And then you will see immediately that the vacuum expectation value of the charge operator matched between two black hole states, denoted by m, is of the order h bar times omega times the square root. And if you evaluate this, you will see that the charges are not anymore 0, but they are of order 1 over n, which means that quantum mechanically the two states q dagger, q hat times n, and n are not anymore orthogonal to each other as it was at the beginning when we were considering basically the classical vacuum expectation value. In other words, for finite n, the charges are non-vanishing since the energy gap is non-zero, and we can also now start to count the charges. To do this, we express the energy gap in terms of the angular momentum of the modes. And if you do this calculation, it turns out that you get that the energy gap is proportional to L square, suppressed by 2 powers of n square. However, in order not to exceed the 1 over n bound, it turns out that the maximal allowed angular momentum is of order square root of n. And then if you count the modes, namely you also consider that the quantum number n takes values between minus L and L, that you get L square equal n different charges. So what is the corresponding entropy? We have just seen that there exist L square equal n different Bogoliubov modes. One can argue that each Bogoliubov mode can be considered as a qubit that carries at least 1 bit of information, and hence doing this, the number of states is roughly of the order of 2 to the n, and therefore the entropy is of order n, which is in agreement with the Bekenstein-Hawking entropy. Furthermore, and I don't have time to discuss this, one can use this model also as a universal quantum computer, so these black holes can be described and used to perform quantum computations, as it was discussed in these 2 papers written down here. So I'm basically at the end, so let me end with 2 final remarks. The first remark is that also Minkowski space can be regarded as a near horizon limit of the Schwarzschild geometry, obtained in the limit where the Schwarzschild radius is very big. And therefore, as we have discussed in a paper, it means that in the quantum language the corresponding Minkowski vacua are infinitely degenerate, which we have known before, and can be regarded also as coherent states of infinitely many gravitons with 0 momentum. And this is precisely what is happening for the BMS, for the standard BMS transformations. The second remark is the following, namely that this picture, and this is something which we want to elaborate on also in the future, relates nicely, as I think, to the S-matrix picture, namely to a computation which we have done about 2 years ago, and which I have presented at the last string conference, namely the amplitude which describes the scattering of 2 gravitons into n gravitons in a particular kinematical regime. The kinematical regime is such that the gravitons in the final state precisely have momenta of order of the inverse Schwarzschild radius, so they are not completely soft, but they are as soft as the A modes are. But one can also show that at least in a particular kinematical regime, that the ultraviolet degrees of freedom of the string theory apparently do not affect the A modes. And one can see this or prove this showing that the field theory amplitude precisely agrees with the string theory amplitude. So basically, I think that's what I wanted to say. So thank you very much.
Now, time for questions.
Hi. So if I understand what you're saying, then at infinite n, these things you're talking about are diffeomorphisms in the bulk. So usually we say that they don't send states to other states, right? I mean, you said the charges are zero, right? So I mean, they're just, I mean, they're not, I mean, they're zero.
Yes.
So and then the idea is that they stop being diffeomorphisms at finite n, but I mean, because of the level, the exponentially small level spacing.
No, I think that's not precisely what we are saying. I think also at infinite n, there are diffeomorphisms at the boundary or at the horizon. The associated charges are indeed zero. And I think this is also an agreement, if you remember Malcolm's Paris talk yesterday. It simply comes from the fact that we are considering static configurations. So there is basically no time dependence. So performing this integral relevant for the charge, you get zero. But it does not mean that we are considering charges inside the bulk. The charges, I think, still live at the boundary, at sky minus, or at the horizon. But nevertheless, they are zero. But I think there is no contradiction. It simply shows you that at the classical level, if you compute, or turning this into the quantum language, if you compute the classical vacuum expectation value of the charge operator that is defined on the boundary, you get zero. And only if you consider finite n corrections, you will see that the charges are non-zero.
More questions?
It seems that the software interpretation for the microstates of black holes almost impossible to be verified through observations or other experiments. Do we accept this interpretation as physical or purely philosophy?
Well, in disguise, this question was also asked yesterday, I think, by Juan, who was asking whether, suppose the LHC can produce black holes, whether one can discover the hair. The problem is that in any physical experiment, one applies an infrared cutoff. So to see these modes, one really has to go to the very deep infrared. And I don't really know, or I cannot really imagine an experiment how to see these charges also in an astrophysical black hole, because the decay time, as you know, is very large. So the only possible hope would be to study analogous systems in experiment, as people in condensed matter physics are contemplating about, or if one is lucky, really producing black holes at some future high energy accelerators.